Hello. Hi, everybody. I'm Diego Marcheggiani, and this is a joint work with Ivan Titov. It's about encoded sentences with graph convolutional networks for semantic role labeling. So the contribution of this work are syntactic graph convolutional networks. And it's basically a new, simple neural architecture for encoding syntactic information in neural networks. With this network, we are able to get state-of-the-art models for semantic role labeling in English and Chinese. Before we delve into the model itself, let's recap what semantic role labeling is. It's the task that consists in predicting the predicate argument structure of a sentence. So if we have this example sentence here. We first discover and disambiguate the predicates of the sentence, makes, repairs, and engines. And then we identify the arguments and label them with their semantic role. For example, for makes, we have the argument A0 that is sequa, that is the creator, and engines, that is the argument A1, that would be the creation. And we do this independently for each predicate. We identify and label the arguments. So in this particular work, we take in consideration a particular flavor of semantic role labeling, that is dependency-based semantic role labeling, where only the head of the argument is labeled as such. We take in consideration each predicate independently, so we can treat it as we can treat the task as a sequence labeling task, and we only focus on argument deification labeling. We take a predicate as given. There are two main lines of work in semantic role labeling nowadays. There is one that basically use systems that use syntax, but they're kind of simplistic, like Fitzgerald told that use only maximum layer perceptron, or Rotel-Lapata that encode dependency paths, syntactic dependency paths with an LSTM. Recent model, though, ignore completely the linguistic structure, so they don't take in consideration any kind of syntax. But everybody knows that in semantic role labeling, syntax is important. So as you can see from this example, semantic dependencies are mirrored into the semantic graph. The creator and the creation are the subject and the object. Unfortunately, or fortunately for us, not all of them are so obvious. Syntax-semantic interface in general is not so trivial. So that's the reason why we need a model that is flexible and it's able to encode these non-obvious examples. These models that the one that we propose is graph convolutional networks. This is basically the outline of my talk. I'll talk first about graph convolutional networks in their original formulation given by Kipf and Welling. Then I'll show you an extension to syntactic trees, syntactic GCN, and how we use it in a semantic role labeling model. Then some experiments and conclusion. So whoa. Was it me? No. Graph convolutional networks are a neural architecture that are able to represent nodes in a graph given the graph structure. They can also be seen as a message passing algorithm. What do I mean with that? Well, let's see an example. Let's imagine that we want to represent the blue node in the context of this graph. So what we do first is to send messages from the red nodes and to get the neighborhood, to learn the neighborhood of the node. And then we send a message from the blue node to the node itself with the green arrow. We take all these messages, we combine them, and we have the new representation of the node that is aware of its neighborhood. More formally, the update rule looks like this. We have that each node is a vector, and the message is a linear transformation of this vector. We have a self loop that is basically information about the node itself, and information coming from the neighboring nodes. We sum all these messages, and then we pass it through some linearity, and we have the new representation of the node. This is an update for a single node, but we have to do it for each node in the graph, right? So let's start from the beginning. We have an initial feature representation of nodes, and what we do is independently send messages for each node. This operation can be done easily in parallel, and it's super fast, can be super fast. After that, we apply some nonlinearity. We can apply again this GCN operator, and the reason for doing so is to enlarge, to widen the neighborhood of the neighborhood of the node. So basically, we take in consideration nodes that are, say, 2 hops of distance from the original node. We apply nonlinearity again, and in the end, we have the same graph structure, but each node is enriched with information coming from the neighboring nodes. This is fine and good when we have a undirected and unlabeled graph, but if we want to apply this to a syntactic tree, for example, that's not enough, because syntactic tree is labeled and directed. So in this work, we extend GCN for dealing with syntactic dependency trees. Let's start with a simple example, a simple sentence. So we have that each word is represented with a vector, and it's basically these words are the nodes of our graph, and the graph structure is given by the syntactic dependency tree. As before, what we do first is to send a message from the node to the node itself. Information, we take in consideration first the information of the word itself. After this, we send messages following the direction of the syntactic tree. But since it's not saying that syntactic information only flows in the direction of the syntactic tree. So for this reason, we also send messages in the opposite direction. As you can see from, hopefully, as you can see from this schema, the messages are dependent on the direction and the label of the args. This can be problematic. We will see it later. So after that, we have sent all these messages. We sum them together. We pass them through some linearity. Bam! We have the new representation of the word that it's aware of its syntactic neighborhood. Like before, we can have more than one layer of graph convolutional network, and in this way, basically, we capture a broader syntactic neighborhood, and the word, each word will be aware of syntactic neighborhoods that is wider. Formally, this is the update rule that we use. We go through the syntactic neighborhood, considering also the self loop, the word itself, and we sum over all the messages. The message, again, it's a simple affine transformation. And one thing, what I told you before, is that each message is direction and label specific. This means that we have full matrix for each label and direction. We have about 50 labels in the syntactic dependency tree in English. Times 2 would be 100 labels, 100 matrices. That's way too much. It didn't even fit in memory. So this model is also over-parameterized. So we had to find some sort of approximation for this. And what we did is to drop all the label information from the full matrix, only taking consideration the direction. The syntactic information, it's only kept in the bias of this transformation. Other problem that we can counter is that not all edges of the syntactic tree are equally important. For the task extend, some some args could be totally useless. But more importantly, we should not blindly rely on predicted syntax. Even though syntactic parser nowadays are pretty accurate, they still make a lot of mistakes. So in order to outcome these two little problems, we introduced edgewise gating. So for each gate, for each message, we decide how much this message is important for the final representation of the next node. So we send a message to the gate decides how much important this message is, and then we sum up everything just like before. The gates are calculated depending on nodes and edges. Good. We implemented very simple model that is composed of, for semantic role labeling, that is composed of 4 simple layers. A word representation layer, bidirectional, LSTM, then the GCN encoder, and then a local classifier on top. The word representation, we represent each word as a pre-trained word embedding, like low or word2vec, concatenated with a random initialized word embedding, post-embedding, the embedding of the lemma of each predicate, and finally a predicate flag that just says if the word taken in consideration, if the word is the predicate taken in consideration or is just or not. This word representation is used as input for bidirectional STM encoder that encodes each word with its left and right context. And this word we used several layers of bidirectional STM. On top of this, we have our syntactic GCN. What it does is to add, first of all, syntactic information to the sentence, to the sentence encoding, and it also adds skip connections between words. So basically, we hope that what is not long range dependencies that are not captured by the STM are captured then by the syntactic GCN. On top of this, for our final semantic role classifier, we have a simple local log linear classifier that calculates the probability of a role given the candidate argument representation and the predicate representation as given by the syntactic GCN. Okay, let's see some experiments. We use the Connell 2009 dataset on English and Chinese, and we use F1 as evaluation measure. All the hyperparameters are tuned on the English development set, and we use state-of-the-art predicate disambiguation models for predicate disambiguation. We didn't take in consideration, we didn't work on predicate disambiguation this time. So, first of all, I want to show you some ablation experiments and see what's the impact of different few hyperparameters that we took in consideration, mostly how many layers of GCN. So we start with a model with bidirectional STM only, without any kind of syntactic information. When we add GCN without any gates, a layer of GCN without gates, we got this improvement. That's good. Then we added some gates because of the problem that I told you before. And we got even more improvement. And at this point, we were super happy. We felt invincible. We were on top of the world, and we thought, okay, let's add another layer. What can go wrong? The sky's the limit. No, it didn't. This was kind of unexpected. But so the reason of this is that 2 layers of GCN probably capture the same information that the LSTM capture. And adding another layer, a 4th layer of GCN, makes the training more difficult. That's why we have these performances. We tried without LSTM, and we were able to get improvements up to 3 layers of GCN. So the idea is still valid. There is some interaction between LSTM and GCN that is kind of tricky, But there is another paper later today in which we used LSTM and two-layer GCN, and that worked a little bit better on the machine translation task, though. So in the end, we used only one layer of syntactic GCN on the rest of the experiments. So in the English test set of the Cornell 2009 dataset, we compared ourselves with the state-of-the-art models. The first three columns are all neural models, and the first two are syntax-aware model, while the third one is syntax agnostic. It doesn't use any kind of syntax. We are able to outperform the state-of-the-art with our model. We also tested on the out-of-domain, and with the out-of-domain, we weren't able to outperform the state-of-the-art. The reason of this is that the Marcheggiani et al., the third column, the state-of-the-art, is syntax agnostic. It doesn't use any kind of explicit syntax. And in out-of-domain, this is better, because basically they don't suffer of any kind of downstream cascading errors from the syntactic parts. So yeah, but nonetheless, we got better than the previous state-of-the-art. We also tried to ensemble our model, like other works in the previous works did, and with a product of expert approach, we got extremely good results, I would say. And basically, these are the best reported score on the English Cornell 2009. We also test on the Chinese test set, and we got very good improvements out of this. Almost around 3 points F1 more than the previous state-of-the-art. So we also tested long-range dependencies. If the idea that we had that putting a GCN on top of LSTM would have gave us some more expressiveness for long-term dependencies. So we basically calculated the F1 as a function of the distance of the argument to the predicate. And what we can see, so the dashed line is the model with the syntactic GCN, and the other line is the model without any syntax. And as you can see, we get a little bit better on arguments that are farther from the predicate. This means that probably we're able to capture long-range dependencies a little bit better. To conclude, we proposed a syntax-aware, state-of-the-art model for dependency-based semantic role labeling. We got state-of-the-art performance on English and Chinese, and we did this using graph convolutional networks for encoding syntactic structure into neural networks. The interesting thing about this model is that you can encode semantics, coreference, and discourse as other linguistic structure into your neural network. If you are still interested in GCN and syntactic information into neural networks, you can go to see our paper in this room at 3:40, and the code is out there. You can download it and play with it. I will be very happy to give you feedback. And yeah, my group in Edinburgh is it's also hiring postdoc and PhDs. I think that the deadline is tomorrow, so maybe it's a bit late. But yeah, thanks. That's it.
Thank you. Questions? Yes.
Hi, I have two really quick questions. Diego, great talk. Which parser did you use? And second question is, think you mentioned that you tried it without using BiLSTMs, but then set up the k equals 3, but you didn't mention what the performance was. So if you just use the GCN cold without BiLSTM, how good do you get?
It is not good. LSTM is extremely important to encode the information into the sentences. There are results on the paper. I didn't report it here, but it's way lower. Something like if that one is 88. Sorry, it was on the development set. If that one was yeah, around 86, the other was 82 or something, was bad. Without any LSTM was bad. And the first question was?
Yeah, you use a syntactic parser. Which one did you use?
I used Kipper, Vass, and Goldberg. Bidirectional LSTM parser was state of the art at the time.
Give it a month. Yeah.
Thanks. Thanks for a really nice talk. I like what you're doing. I'm Martha Palmer, University of Colorado. So I just want to caution you to be a little bit careful about when you're describing what other people are doing and you say they're doing semantic role labeling without any syntax.
Yeah, I know.
Because the training data actually defines constituent boundaries.
Yeah, I should have said explicit training syntax. Yes.
Yeah.
Totally agree. Yeah.
Thanks.
There's another question. Annette? Okay. Was there any other? Okay.
Hi, Annette Frank, Heidelberg. Thank you. It's a very nice talk. I like the approach. I was just curious about your state-of-the-art results. You worked on the 2009 shared task corpus. Other work has worked on 2005. So can you say something? Did you try on both corpora?
Nope. I've been trying only on the 2009, unfortunately. Yeah.
It would be good for comparison to work on both corpora.
Thank you. I'll take that into consideration.
We have time for another quick question. I have a very quick question. So, do you have insights about the relationships between the syntactic relations and the semantic relations for the specific frames you're working on?
So there is we have a small analysis about this on Chinese on the paper. I also did it in English, but in English didn't give a very meaningful, not meaningful, but yeah, it was weird. So let's talk about Chinese. There are some labels, some syntactic labels that when dropped are, so basically we trained our model, then we tested dropping some of the labels of the args, and we found out that dropping one specific label in Chinese, that it's the complement arg, gave us a drop of performance. The reason is that that particular label is very important. So it's a very good indicator of the predicate argument structure. It's Chinese. We had to ask to a native speaker why the reason of this, but yeah, there are some args that are more important than the others.